Okay. Hi, everyone. This is the meeting for the Unit 2 review. This review will be over the entirety of Unit 2. So that's lectures 9 through 16. I'll mainly be concentrating on the second half of the unit because that's all of the newer material. First thing I'm going to do is go ahead and do a share screen situation so you guys can follow along with me. Okay. All right. Now at this point, you should be able to see my screen and you'll be able to go over the review questions with me. If there's anything that you want to discuss beyond just the standard review questions in Moodle, definitely please bring it up and we'll go over that too. You know, I want this to be as useful to you guys as possible. I guess the first thing I wanted to share now that I'm definitely presenting, okay, yeah, I'm doing my screen, is going into Moodle here. I wanted to show you guys that, as you know already, we've got the new lecture links. They've got the transcripts embedded in them, so you can use them or not use them, turn captions on and off. So that should make it a little bit more user-friendly for you guys. If you go down to pass the Unit 2 mini test label, this is a new review video. It goes over all of the same material as the review video that was up here before. That one was from a couple of semesters ago. I just re-recorded it, you know, so if you find the new material, you know, easier to understand than the old material, then you might want to go back over, go through that. It essentially just covers questions 1 through 3 out of the review questions. So then as we scroll down a little bit more, this is all the material that we hadn't covered yet as far as a review. So that's lectures 13, 14, 15, and 16. And then keep scrolling and we get to the Unit 2 review questions, the whole sheet. And this is where I'm going to post the review video that I record today. Of course, you will have already accessed that. So I went ahead and pulled this up already. And this is the review questions 1 through 3 we did in the other video. So you can go through the other video to get an idea of what's going on with 1 through 3. We'll concentrate on the questions pertaining to the new material today. So let me just check back with the group chat real quick, make sure I'm not missing anything. Now just have a few more people have joined us live. And as always, just go ahead and text, you know, right here or take your mics and put them back on if you have any questions. So, oh gosh, this is probably the most important thing. And I know I posted this in the group me, but I just want to bash everybody over the head with it over and over again because I don't know, like 40% of the class got this wrong on the mini test. And it always just breaks my heart. Okay. There is exactly 1 star in the solar system. You will see that question from the mini test verbatim on the unit exam. How many stars are in the solar system? The correct answer is 1 star. So, I mean, no matter how many times I mention this in a review, somebody's going to get it wrong, but hopefully it'll be fewer this time because I'm really trying to bash everybody over the head with it. So I'm throwing that out there. I also added to the group me some other kind of big takeaways from the mini test. So I would go back and maybe access that, look at it if you didn't do as well as you liked, you know, and you know, those were some of the concepts that maybe a lot of people missed. Things like the difference between a variable and a constant, this whole idea of what is in the solar system, what is outside of the solar system, and so on. So I just wanted to mention that first before I forgot to go back and talk about it. I'll come back over here now. And like I said, we did 1, 2, and 3. 1 essentially comes from lecture 9. It's essentially just, you know, describe the, you know, big bad dudes of astronomy and talk about their contribution to the science. So, Ptolemy, Copernicus, Galileo, etc. And we did that as part of the last review. To describe Newton's 3 laws of motions, how do they apply to motion in space? So things like surface gravity, escape velocity, are all highly dependent on Newton's 3 laws of motion. And then 3, how did the solar system form? So 4, and then 3 is really out of like lectures 11 and 12. And those 2 lectures are probably the most integral to this entire unit, because everything else that we cover is just sort of niche specifics, where we kind of expand on some of the concepts from 11 and 12. Now, one of those is the idea that impacts form planets, and a really big impact led to the formation of our closest celestial neighbor, and that's the moon. So question 4 here is, describe the most likely theory on how our moon formed. Now, when we're talking about the actual dominant theory, and not some of the kind of crazier crackpot theories, it's always going to go back to what we call the giant impact theory. So in the giant impact theory, the idea is that we have collisions between objects that have formed all of the planets, terrestrial and Jovian planets, and that there were some unknown number of things that are sort of similar to terrestrial planets that we have today. And the way that you condense that down to just having 4 terrestrial planets is because some of those objects are inevitably going to be sort of crossing each other in orbit. And when you have something that's orbited around the sun 4.5 billion times like the Earth is, of course, it's going to have impacted basically anything that could be part of its orbit. So if it's possible for objects to have collided, it's probably going to have happened already. So the idea is that at some point in the past, you had some big rogue object, something similar to maybe Mars, something maybe similar in mass and size to Mars, that was existing a little too close to Earth. We don't know if it was closer to Mars, closer to Venus. There's really no way to kind of back calculate quite that far back, but just that you had this secondary object that was on a collision course with Earth. It collided with Earth at a really low angle, and that enabled most of the mantle of that object to be cascaded back off into space, most of the core of that object to actually be absorbed within the Earth. So in the giant impact theory, you have a low angle impact between a Mars-sized object and the original Earth that both led to the formation of the moon from the mantle material that was ejected into orbit, and it led to an increase in the size and mass of our planet. So the idea behind the giant impact theory is that it accounts for the unusually large size of our moon compared to the size of our planet. It's not really that unusual to have a moon that's maybe much, much smaller than the planet itself, because then you can account for it by having some sort of capture theory. So that would be an example of a non-dominant theory. Capture theory. Essentially, the problem with the capture theory is the moon is too large. Our moon is too large. Another potential theory, well, I guess I do say what are some of the earlier theories. I guess I'll go over another one. But essentially, the capture theory doesn't work because the moon is too large in comparison to the size of our planet. Something like the fission theory. just basically has no evidence to support it. So essentially with fission, the idea is that you have material that was actually originally part of the Earth itself that somehow became detached to form the moon. So we've never really seen any process like that happening. You'd have to have something like an insanely fast rotation of our planet and some kind of other secondary force to actually make material be ejected from the surface of the Earth and coalesce in orbit. So it's sort of one of the more kind of crazier theories, just because you don't really have any kind of supporting evidence for it. So that's basically the gist. If you go through, and I believe this is the question that is related to the extra credit assignment. If it's not this one, then I switch them up every semester, so I always confuse myself. It's probably something like, how did the solar system form? Then essentially you just want to make sure that you've covered the main explanation of the dominant theory and at least maybe one of the others. You don't really need to go into several theories that are not either supported by evidence or don't really match up with the evidence. So that is the moon forming impact. It's certainly not the only thing that you need to concentrate on from the moon lecture. I had someone asking about the moon lecture just in email, and they were basically talking about the challenge in memorizing some of the stuff in that lecture. When you start talking about the rising and setting times of the different lunar phases, or the what we call meridian crossing, like when the moon is directly overhead for each of the different moon phases, none of that is anything that you need to actually memorize for the exam. I would know the lunar phases. I would know how some of those phases match up with things like eclipses and tides, and what other kind of conditions you would need for stuff like eclipses. That's most of the main concepts from that moon lecture, and that's lecture 13. So I'm going to scroll back over to the review for just a second, make sure no one's saying like, hey, your mic cut out or something like that, or anybody had any other questions. Looks like we're good. So I'm going to come back over here. Okay, the next question, question 5, describe the similarities and differences, so it's a loaded question, between the terrestrial planets of our solar system. What are the characteristics of Earth that allowed it to be habitable while the others are not? So 2 separate questions. It's basically just, almost everything from lecture 14 can be crammed into this question in some sense. Now, I don't think we're going to try to cram everything into it. I'm just saying theoretically you could. So similarities and differences between the terrestrial planets. The first thing that you need to know for this question is, what are the terrestrial planets? They are an increasing distance from the sun, Mercury, Venus, Earth, and Mars are the terrestrial planets of our solar system. And when you start talking about their similarities and differences, probably the most stark difference is in terms of size and mass. And they vary somewhat in terms of size and mass. And that variation in their size and mass is going to relate back to their capability of maintaining geological activity, because mass means more retention of heat. More retention of heat means more surface evidence of that heat, and that's where the geology comes into play. So they vary somewhat in terms of size and mass, which in turn relates to their ability to sustain geological activity. In terms of size, mass, and geological activity, or almost in a sense like whether or not the planet is alive, Mercury is the least active, also the smallest and least massive. and then Mars, which shows pretty decent evidence of geological activity at some point in the past, but currently isn't really maintaining that geological activity. So there are no active volcanoes on Mars. There's no active plate boundary systems. There's no active magnetic field, which has led to the degradation of the planet's atmosphere and its ability to retain water on the surface. So Mercury is the least active, and then Mars, and then Venus, followed very shortly by Earth. So Venus and Earth are almost as close to twins as you have in the terrestrial planet systems. They're really similar in terms of size and mass. Earth trumps Venus just a little bit. It's just a little bit more massive, a little bit more larger in terms of radius. And it's a little bit further away from the sun, which with that and its amount of carbon dioxide in the Earth's atmosphere has led to much better conditions on Earth than you have on Venus. Now, so the second part of this question, what are the characteristics of Earth that allowed it to be habitable while the others are not? Habitability is most related to the ability of a planet to retain water in a liquid form. Earth is in the habitable zone of our solar system. So essentially, if it were any closer to the sun, conditions would be too hot and it wouldn't have an ability to maintain liquid water on the surface because that water would be forced to be in a gaseous state. So then you essentially just don't have liquid water on that planet. And at least in our terms of life, water is critical for life. Now, if we were any further away, if we were, somewhere along the different distance of maybe Mars, maybe a little bit further away, like the asteroid belt, then the planet is too far away. And then that water can't exist in a liquid form because it's going to be in an icy form. The other aspect of Earth that allows it to be habitable while the others are not is its ability to retain geological activity. So geological activity is also critical for the habitability of a planet because it allows that planet to retain an atmosphere. So if you want an example of when that goes wrong, think unlike Mars. So I think that's a pretty decent, potentially grammatically incorrect sum up of lecture 14, at least the really big important points. So the whole idea behind lecture 14 is that go through some of these surface features of a planet that give us an indication of its geological activity. And then we start going around sort of like ranking these planets in terms of their ability to maintain geological activity. And I cover the planets in this sequence in the lecture. I cover other things about the planets too, but probably the first and foremost thing that you need to concentrate on is its ability to maintain geological activity on account of its size and mass. So that's why we cover Mercury first, and then Mars, then Venus, then Earth. And then as we cover Earth, we talk a little bit about what makes it special, what makes it an oasis of life. So that's question 5. Going back over here, making sure no one has any questions. It looks like everybody's good. So coming back over here again. Now we're going to get into the next one, which is essentially the same question, but pertaining to the planets in the next lecture, which are Jovian planets. So the question is, describe the similarities and differences between the Jovian planets of our solar system. Why are some of them larger and more massive than others? So this is kind of the follow-up question. It's similar to what makes Earth special. Why are some of these larger and more massive? Now, it's a completely different beast when you're talking about Jovian planets, and that's why we categorize them completely different. Because once you reach this threshold of a planet where it can start retaining hydrogen and helium in addition to all of the other gases, then it's essentially just an entirely different, almost organism in a sense. So first off, let's discuss again, what are the Jovian planets? So the Jovian planets of our solar system, and the reason we call them Jovian is because they're the Jupiter-like planets. Earth is the king of the terrestrial planets. Earth is Terra, so terrestrial. Jovian is derived from Jupiter. So the Jupiter-like planets of our solar system are, of course, Jupiter, Saturn, its nearest neighbor and second largest planet in the solar system, and then Uranus and Neptune. These planets are found in our solar system to be more massive with increased proximity to the center of our solar system. I use the word solar system a lot in this sentence, sorry. Okay. So I'm sure there's a better way to put that, but that's okay. These planets are found in our solar system to be more massive with increased proximity to the center. So that's your biggest tip off to sort of why some of these became more massive and some of them are less massive. We think that proximity to the center of our solar system and potentially like an aspect of timing are two of the most important equations to figure out sort of like why some of them retain lots and lots of gas as part of their atmospheres and why some of them retain significantly less gas. It's all an aspect of where they are to be found in our solar system. So take, for instance, this is the sequence in which they're found. Jupiter is about 5 times further away from the sun than the Earth is. Saturn's about 10 times further. Uranus is about 20 times further away from the sun than the Earth is. And Neptune's about 30 times. So there's lots and lots and lots of distance between all of these solar system bodies. There's a tremendous amount of gas to be found in the early stages of our solar system before the solar wind sort of cleared the air. And if you have a massive enough planet, then you can start to retain that gas. But the trick is all of the Jovian planets contain not just rock and metal like the terrestrial planets, but also hydrogen compounds, which is just a fancy way of saying various types of ice. As part of their solid interior structures. So that's probably the biggest thing that makes a Jovian planet, not a terrestrial planet, is it's found far enough away from the center of the solar system that it's cold enough to start to take some of these compounds and actually turn them into a solid, as opposed to liquids and gases, as they're more often found on the terrestrial planets. So you have all of these different types of ice, and not just water, but methane and ammonia and effectively dry ice, which is CO2, all of these things found in a solid form that are way more abundant than rock and metal, so you can build a much, much more massive interior. And that more massive interior is something like the equivalent of 10 Earths, all stacked up on top of each other. And they all start off with approximately that building block. That's what their cores look like underneath all of that hydrogen and helium. Then the differences between the Jovian planets is most likely accounted for by their proximity to the inner solar system and the timing of their formation. So then Jupiter is the most massive, followed by Saturn, and then technically followed by Neptune and then Uranus, but they're so similar in size and mass that we can almost kind of assume they're almost like twins, followed by Uranus, Neptune. And so that's why Jupiter's 300 times more massive than the Earth. Saturn's only 100 times more massive than the Earth. And then Uranus and Neptune are closer to maybe like 20 times as massive. It's just a matter of how much hydrogen and helium gas you're retaining on top of those nearly identical cores. The other major distinction, and something that I talk about a lot in the lecture, is the moons of these planets. But since I'm talking about the planets themselves in this question, I didn't really go into the moons at all. But the moons are potentially more interesting objects and more Earth-like objects than the planets themselves. You know, they're just moons because they happen to orbit a planet instead of a star. So I spend a lot of time talking about the moons as well. And I'll just kind of jot down on here for you. But even though I talk about a lot more of the moons than this, I could tell, you know, maybe kind of mention them. I think the most important ones for you guys to know for the purpose of the exam are the Galilean moons of Jupiter. And those are the moons found by Galileo. So that's Io, Europa, Ganymede, and Callisto. And Saturn's biggest moon, called Titan. Those are the ones that I spend a lot of time talking about in the lecture. Those are the ones that I would know for the exam. I would mainly kind of concentrate on these as a cluster, the Galilean moons. The idea that why is Io so much more active than Europa and so on and so on. It's Io's proximity to the planet. So there's this similarity between Jovian moons and terrestrial planets, where Jovian moons are effectively just, you know, these objects that are almost planet-like, but their source of energy is very different. It's how close they are to their host planet and how much the gravitational pull between the planet and the moon is tearing them apart. It's the tidal heating thing. Whereas the source of heat on a terrestrial planet is different. It's remnant heat from the creation of that planet. So, yeah, that's just something that's not really asked for in the question. It's just something I wanted to kind of mention because, you know, I talk about it a lot in the course of the lecture. So, okay, I think that should probably be it for question 6. I'll come back over here for a minute, make sure that you guys didn't have anything. Looks pretty good. And we'll finish this out with the last question. The last question relates to, let me try that again. The last question relates to lecture 16, and lecture 16 is kind of my miscellaneous lecture. It's everything that I hadn't gotten to as far as describing objects in our solar system. In 11 and 12, I talk a lot about the formation of the sun, and in the next unit, I talk about stars in more detail. So we'll talk about the sun even more then. In lecture 13, I talk about the moon, 14, terrestrial planets, 15, Jovian planets. So then I have all of these other objects in our solar system that are much more numerous, but they are tiny objects. So that's why we have this kind of miscellaneous object lecture. This is where I talk about asteroids, comets, meteors and meteorites, and Kuiper belt objects, and Pluto would fall into that category. So the numerous miscellaneous itty bitty bodies in the solar system. So the question is, what is the difference between comets and asteroids? Where do these objects reside in our solar system, and why are they limited to these environments? So comets are to Jovian planets as asteroids are to terrestrial planets. They're effectively just sort of the miscellaneous small leftovers in the planetary accretionary process. So let's talk about these individually. Asteroids are effectively leftovers in the process of forming terrestrial planets and exist in the aptly named asteroid belt that exists between Mars and Jupiter. And it's not coincidental that it does exist next to Jupiter, which exerts this huge gravitational pull and keeps things sort of mixed up enough that as Jupiter orbits around the center of the solar system, its gravitational pull pulling against these asteroids almost is enough to sort of fight the gravitational pull of the sun to a certain extent, and it keeps those objects from coalescing and forming another planet, or maybe another like little planetoid, because there's really not that much material out there. It's just a lot of little pieces. So asteroids are composed of asteroids, which are composed of rock and metal, are leftovers in the process of forming terrestrial planets and exist in the asteroid belt between Mars and Jupiter. They are effectively restricted to that environment because if they were anywhere else, they would just be comets. Because in addition to the rock and metal, you would have other building blocks. Comets are really similar, but they're more plentiful and more numerous because you just have more stuff to build the comets with. Comets are composed of rock, metal, and most importantly, all the same kind of ices. So that's water, ammonia, methane, that Jovian planet cores are made out of. And so the composition of a comet is almost like a really densely packed, dirty snowball. It's just a chunk of ice, rock, and metal. And they have to exist somewhere in the solar system where that ice isn't going to melt or sublimate. Melting is just the process of turning that solid into a liquid. Sublimation is when you skip the center step and go straight from a solid to a gaseous state. And so when comets dip into the inner solar system, they're almost on a suicide run. In some cases, they are on a complete suicide run through the inner solar system. So comets are composed of rock, metal, and various types of ice, all of these different ices, and exist happily, we'll say, in the outermost solar system in the Kuiper belt. So that's just outside the path of Neptune, and that's the outer part of the inner solar system where things tend to orbit around a little bit more normally in a circular orbit that still follows the basic path of the planets. So it's still on the sort of kind of central disk of the solar system. And then the Oort cloud is anything outside of that that has really, really erratic orbits. So super inclined orbits that kind of dip in really close and they're really far away, and or orbits that tend to get out of the tilt of the rest of the planet. So if this is the tilt of the rest of the planets, these objects out in the Oort cloud tend to just have really super inclined orbits. So they exist happily in the outermost solar system in the Kuiper belt and the Oort cloud. Comets that enter the inner solar system become destabilized by the heat from the sun and either completely degrade or are damaged by their time in the inner solar system. And so that is when you get to see the comets that actually have these bright ionized tails. So when you have comets that are actually visible from Earth, particularly without the aid of a telescope, these are comets that have actually entered into the inner solar system, are in this process of completely breaking apart. Either they completely get destroyed or they're going to become partially destroyed. So something like Halley's Comet is one that does get into the inner solar system, but gets in and out of the inner solar system quick enough so that it is not completely demolished by its time here. So it's when these comets are in the inner solar system, this is when they grow tails and are highly visible objects from Earth. Last thing I'll mention about these comets, it's the process of degrading and destroying these comets in the inner solar system that leaves stuff behind that rains down onto the Earth as meteors and meteorites. So you don't really have all of that garbage left behind in Earth's orbit naturally, unless you have something that is continuing to sort of place stuff in our path. And that's what the comets do. So most of the material that eventually rains down onto the Earth as meteors and meteorites, especially now, 4.5 billion years after the Earth formed, it's usually remnants of comets. Okay, so that's all I'm going to say about comets and asteroids. It's not everything that we talked about as part of this lecture, as usual, but it's, you know, like I try to cover with these review questions, kind of the main gist. So coming back over to the review and ending the presentation here, I just wanted to kind of open up one more opportunity if anyone had questions. All right, cool. I'm going to go ahead and stop the recording now.